Ladies and gentlemen, welcome. This is a big-ass room. I've got lots of stuff to play with. If we get bored, we can have a game of basketball, apparently. There's a basketball over there. All sorts of things. There's nothing coming up tomorrow that's particularly on your minds, is there? Okay, I guess there is. This is the Monster Marathon Midterm Madness Review session. It is going to go for probably 4 hours, but if you all stay and ask me intelligent questions that have something to do with Math 201, I will stay until we all fall asleep or over or something like that. Okay, so that's the general overview. I'm going to spend about an hour on the last couple of topics, which are Lagrange multipliers and Taylor series, maybe even less, because what I'd really like to do is then embark on a complete survey. It's not going to be a review, but it will just be a summary of the things that you ought to know, the most common types of problems in particular. So I'm going to try to lay that all out for the second hour, and then we'll take a break for a little bit. And then when we come back, we will look at problems. So you have hopefully done a whole bunch of past exam problems, practice problems. I know there are some solutions, but some of them are not clear. Some of them don't even seem to match up with the actual problems. Don't blame me. But together we'll sort out whatever you want. All right, so that's the basic attack plan. You can come and go as you please. That's the drill. You can ask me questions. Is this thing too loud? Does it sound okay? All right. Are there any general questions before we begin? Something, not so much a math question, but about the exam or something like that, something that's on your mind? No? All right. So without, oh yes, we have one up here. Shh. What is the average on the exam? Well, you haven't sat it yet, so how do I know? No, I mean, look, the average is whatever it is, right? I mean, if it's a harder exam, the average will be lower. If it's an easier exam, it will be higher. Or if you're all really good and you all get, 90%, I'd love to see it. I have never seen it in any of these courses, but if you all got above 90, this would be great. So yeah, I don't know. The fact is you will get a letter grade for the course, for the midterm, but then it doesn't really have any meaning. It's just a guide. The real calculation is done at the end after you've done the final. Okay? Another question over here. Is time a huge issue? Well, here's a question. I know you've still got a day or so until the exam, but did anyone actually try taking one of these past midterms under exam conditions, by which I mean 90 minutes of actual sitting there, no book, no interruptions, etc.? Anyone try that? We have one. Okay. So I advise you all, if you can possibly, no, this is good. I mean, I advise you all to try it before tomorrow. And the same thing goes for the final. By the way, you should try to save last year's or last semester's midterm and final for that purpose. This is the best advice I can give you in any math course. If you have access to last year's or last semester's one, for goodness sake, do it under exam conditions. No phone calls, no food, just on your own honor. Don't cheat yourself. And that's the best way to simulate it. But that said, historically, I believe that time has not really been the issue. That's not to say that everyone finishes. By the way, I've seen people leave early and miss a question. Maybe they forgot to come back to it. So a little piece of advice, if you skip a question, that's fine. Don't just somehow remind yourself to come back to it. I don't know, bring some dental floss and wrap it around your finger until you've come back. I don't know, write a note, whatever it is. Don't leave a question out and leave early. That's my advice. Any other general questions? All right, I am going to try to use standard chalk because it erases better. If you find you cannot read it, I know it's a big room, I'm just going to use these 3 boards here in the middle. If you're having trouble reading the writing, there are seats closer up, but I'm not going to require that you all move. Just let me know if it's too small. Okay, I'll try to write bigger than I normally do. All right. So, In some sense, this first hour then is the last part of the summary, but obviously in a little more detail. So I will come back and enumerate what I'm going to say, but I think that this is jumping towards the end. Now, I want to talk about Lagrange multipliers. Before I do, I kind of was in the middle of something last time, so rather than go back and finish that problem that I really had to rush because I ran out of time, I think what I'd like to do is just talk about maximizing and minimizing in general, and then tell you about Lagrange multipliers. So when it comes to max and min, you have a function f. It could be of 2 or 3 variables. Of course, it could be of any number of variables, but we've already done the one in single variable calculus, and we don't really do 4 or more in this course, so it's 2 or 3. And we'd like to find the maximum or minimum or minimum values of f on a certain region. Now, if this region is closed, meaning it contains its boundary, and it's bounded, meaning that you can sort of hug it, as I described in the review session a couple of weeks ago, if you can sort of enclose the region in a big circle so that everything's there, that's what I mean by bounded, then it will have a maximum or a minimum. But as we've seen even in single variable, if the region's unbounded, there may be no maximum. There may be no minimum. So a silly example, well, not a silly, simple example. If f of xy is x squared plus y squared, the minimum is surely 0. We don't even need calculus to see that. The only way that can happen is at the origin. But there's no maximum. There's no maximum, because x and y can be as far away from the origin as you like. This is unbounded. It's an unbounded region, and f doesn't have a maximum. So the real kicker is this. If you have a closed and bounded region, then the maxima and minima, well, extreme points together of f occur either at a critical point talk makes a really satisfying crunch in the microphone. Is that actually annoying people? Okay. Cool. Okay, at a critical point of f, and remember, this essentially means, to all intents and purposes, that fx equals 0 and fy equals 0. So this is the partial derivative with respect to x, the partial derivative with respect to y. And if it's 3 variables, you'll also need fz equals 0. So you need all of these to be 0. The other possibility is, or one of these, one or more derivatives does not exist. So it's possible to have a max or a min at a point where the function has a corner or something like that, 3-dimensional, a spike. But generally you're looking to solve that the derivatives are 0. So that's one possibility. The other possibility on the boundary. Now, in single variable, the boundary is pretty easy. If you're working on a closed interval, there's just 2 points, A and B. But here, the boundary, the region may be a region in the plane. It may be some sort of circle, in which case you've got infinitely many points to check in a way. You've got to check the critical points, which may be, say, here and here, and you have to check every point on the boundary. So it's a much tougher proposition. Sometimes you can do this with algebra. So what do I mean by algebra? What I mean is, if you know, for example, that x squared plus y squared equals 3, say this is a circle of root 3. So if you know that's true, you can actually solve y in terms of x and then you could substitute it in and reduce it to a one-variable problem. You see, f would be defined everywhere in here, but on the boundary you can sort of think of it as a function of one variable. It's just whatever this angle is. You could do it in polar coordinates, for example. So there's some flexible. Or you can actually use Lagrange multipliers, thinking of the boundary as a constraint. And more on that in a short while. In fact, very soon, because I'm now going to talk about Lagrange multipliers. If there is a constraint, you have to use Lagrange multipliers instead of this f of x, instead of the critical points. So use Lagrange multipliers instead of critical point. But you still have to check every point. You always have to check the values at each of the points of interest. To see which one is biggest. Or which one is smallest. So the point being that even if you found a critical point, it may not be a maximum or a minimum. It could be a saddle point. And you won't know unless you actually check. So having found, say, 3 critical points, you plug them all in, the actual xy or xyz coordinates, and you find that one of them might be 7, one might be 3, and one might be -4. Well, the 3 is not a global maximum, because there's a 7 and there's a -4. But the point is you've narrowed this infinite number of points down to just a few points, plus whatever's on the boundary. All right, so that's the general idea. Now let's talk about Lagrange multipliers specifically and the method, and then we'll look at a bunch of examples. And I'm sure you'll have plenty of Lagrange multiplier and max-min type of questions that have come up in previous exams later on. All right, any questions before I sort of talk about Lagrange multipliers? Yes. So if you only have one point of interest, the question is, how do you know if it's maximum or minimum? Well, if it is a closed and bounded region like this, then you have to have a maximum and you have to have a minimum. So if you only have one point of interest, you probably made a mistake. Right? It's got to be on the boundary somewhere. Now, this function up here, this has only one critical point, which is at the origin. And you plug it in, you see that it's 0. So how do you know it's a maximum or a minimum? Well, you have to inspect what's going on. We have the second derivative test as well that you could use with the Hessian, but which we looked at last time. But in this particular case, you can see it's going to be positive everywhere. And so there is no boundary. The boundary is at infinity in some sense. So what you have to do is analyze the behavior just by inspection. And you can see here that there's no maximum. So if there's only one point, it had better be only one critical point and no boundary. It had better be a max or a min. And you can tell by looking at any other value, in which case there would, if it's a min, then there's no max. And if it's a max, then there's no min. Okay, does that make sense? Any other questions before I proceed? It's a big room, so I may not even see your hand. If you raise your hand, you're welcome to sort of wave it around so I can see it. All right. Here's the deal with Lagrange. I'll present it in 3 dimensions, what the hey, but of course it works in 2 dimensions if you just ignore the z. So the general sort of framework is this. You want to, so for Lagrange multipliers, Lm, you want to minimize or maximize, so find max or min, of a function f, say, maybe on some region, region R. R stands for region here, not reals, and it could be the whole space. But the difference between this problem and the one I mentioned over here with just no constraint is that I'm going to assume there's a constraint. Which I'll write as g of x, y, z equals 0. Now, if it doesn't look like g of x, y, z equals 0, but some other junk, you can always put everything on one side so that it equals 0. So I want to just contrast here. Here's just a function. I can plug in any three numbers into it, any point in space, and I get a value. But I'm restricting myself to, if you like, a level surface of g, a particular set surface, and that intersection with r. Maybe I don't want the whole of g, maybe I only want a certain part of it. So basically then, the idea is that I don't have the freedom to pick a critical point of f, because the critical points of f may not satisfy this. So the beauty of the Lagrange method, and you know, if I had more time and you didn't have a midterm tomorrow, I would actually go into the theory of it and why it works. I think I will have to just sacrifice that and just get practical, because as I say, the midterm is tomorrow. Don't mean to keep reminding you of that. There's nothing you can do about it. It's going to happen. All right, so here goes. So the method is really quite beautiful. The idea is you try to solve grad f is some scalar multiple of grad g. That's really the meat of the whole thing. So the idea is if you solve this as well as that constraint which has to be true, then basically the max and the min must occur at these points or the boundary. Again, if there's a boundary, they might occur there. So basically the solutions that you get out of this method replace the critical points. That's all. Otherwise it's the same thing. You are not guaranteed to find that any solution in particular is a max or a min. You have to plug it in and check it. So plug in to check. Just like not all critical points give you a solution here, not all of the solutions to these points, these equations, give you max or a min necessarily. They may be a sort of saddle-y type point, although it's more complicated with the constraint in here. Now, what is this actually? This is, let's look at these equations again. So first of all, let's just expand this on here. This is actually a vector equation. There's three components here and three components here. So what it comes down to is that there's actually three equations embedded in this one up here. And here they are. We have fx, the x derivative, evaluated at x, y, z, has to be lambda gx. And then the same with the y coordinate. And the same with the z coordinate. So the z derivatives have to be multiples of each other. And then finally, we still have that g of x, y, z has to be equal to 0. So these are actually four equations and four unknowns. It seems a little unfair that there are four unknowns because we really only started with three, x, y, and z. But the method calls for the introduction of this extra parameter, lambda, which is the Lagrange multiplier in this case. The reason it's a multiplier is because it multiplies all the derivatives on the right there. So we've introduced a new lambda, and we now have four variables to solve for, but we have four equations. So the point being that if you solve to find the triples of x, y, z, at that point the lambda doesn't really matter. You can throw it away once you've found the solutions. Once you've done this, then you have all your possible candidates apart from the boundary points, if there are any. Okay, so that's the general method. Again, if there are two variables and you only have x and y, you don't have a z, then of course you omit the z in all of this, and you won't have this third equation here. So you'll only have three equations, but you'll only have three unknowns, x, y, and lambda. Okay, there's another case where there are two constraints, but I don't want to touch that yet. I would rather do an example. Now, in terms of doing an example, I see no reason why not to ask any of you, if you brought in a Lagrange multiplier problem, maybe from a practice problem sheet or a previous exam, there's no reason not to use it. Otherwise, I'll just pick one. But since you all probably have brought some in, if you happen to want to see the answer to it right away, I'd be happy to take it. I have all the previous exams printed out, but I don't always know. I don't need two microphones here. I don't always know which one is which, so... Well, while you're thinking of it, I'll just do one example first. Okay, here goes. This is from the fall 2004 midterm, and it appears on the review session 6 worksheet. You can ignore all of the rest of the problems on that, though, because they're post-midterm. So it says, use Lagrange multipliers to find the points on the surface. So find the points on the surface z equals x squared plus 2y squared that's closest to, and part B, if you like, furthest away from the point 0, 0, 2. That's a Lagrange multipliers problem, if ever I saw one. First, it has a clear constraint, and second, the problem says use Lagrange multipliers. So all these things have made me suspicious that I should be using Lagrange multipliers, so let's do it. The first thing to notice, and here is a general piece of advice which I'm going to dictate to you, but I suggest you write down and put some sort of box or cloud around it. Here goes. If you ever have to maximize or minimize a distance, do not deal with the distance. Deal with the square of the distance. Always use the distance squared. After all, if the distance is maximized, so is its square, and vice versa. The same thing goes for minimize. The reason being that if you deal with the square of the distance, then there's no square roots. It's just the sum of squares. Much, much easier to differentiate. Why would you want to differentiate square roots if you didn't have to? You wouldn't. So look, here is the deal. We don't have a function f, nor do we have a constraint g. So we kind of have to recast the problem in that sense. Now, here is a constraint. We can't just choose any point. We've got to have a point x, y, z that satisfies this equation. So I'm going to take this equation, I'm going to say this is x squared plus 2y squared minus z equals 0. I put the z on the other side. I'm going to call this g of x, y, z. So g of x, y, z is x squared plus 2y squared minus z equals 0. Now let f of x, y, z, what are we interested in? We're interested in the distance from the point 0, 0, 2. So let this be the square of the distance, as per my advice, between x, y, z and 0, 0, 2. So we need a formula for f before we can do anything, and it's fairly straightforward. The distance between 2 points, you just take x minus 0 all squared plus y minus 0 all squared plus z minus 2 all squared. So it works out as x squared plus y squared plus z minus 2 all squared. All right, so now we have reduced the situation to the one in the theory. Namely, we have to maximize or minimize this function f subject to the constraint that g equals 0. Any questions so far before I actually embark on the methodology? Yes, up the front.
Why is the constraint always equal to 0?
Why is the constraint always equal to 0? The constraint, as I said, doesn't have to be equal to 0 in a way, but if you shove everything over the left-hand side, you can always make it equal to 0, and then that's the way that you really want to do it. Why is it? You're asking why is it possible to put everything on the left-hand side, or why would you want to do it? Well, without justifying the method, I can't really answer your question as to why you want to do it. The fact is that the way the method works, in a nutshell, is to consider level surfaces of f and g and kind of expand them and see what happens there. And you kind of need to see that the normals point in the same direction, which is what that first equation there is. But the problem is that if some junk is on the other side, then it's really got the negative of the derivative. See, if you just put a z here, if you differentiated that, you'd have 1. But here you can see it's minus 1. And so basically you'd have to do the same thing to f for them to be compatible, and the whole thing would just be a mess. So again, it's built into the method, and without proving the method, I can't answer your question. Sorry. That's just midterms tomorrow. Do it that way. Sorry, I've got to be pragmatic here. All right. Any other questions? I know it's not a satisfying answer. I mean, at 12:30 or whenever we're finished, I'd be happy to explain it to you. Or after the midterm. All right. Anyway, sorry, that's a bit ruthless, but what can you do? Here's the f, here's the g. Let's write down our equations. So we need fx. Well, we differentiate this, we get 2x. I guess we'll do all the derivatives. Fy, the y derivative is 2y, the z derivative is 2z minus 2. Repeat for g. The derivative is 2x, the y derivative is 4y, and the z derivative is minus 1, not plus 1. All right, so according to the prescription, we need fx is equal to lambda gx, which means that 2x equals lambda times 2x. Rather than try to solve it first, I want to write down all the equations we've got to deal with. So lambda gy, so we repeat for y, we get 2y is lambda times 4y. And finally, for the z derivative, we get 2z minus 2 equals lambda times minus 1. And then we have one more equation, which is that g equals 0. So we also need x squared plus 2y squared minus z equals 0. And in this case, of course, you could put the z on the other side. That's fine. It's just when you're differentiating it, you need to make sure it's all on the left. All right, so we have to solve those 4 equations simultaneously. I don't really have general advice as to how to solve them. I mean, these are equations that can be quite nasty. In principle, you should try to find the simplest equation first. My mind naturally gravitates to this one. So if we cancel out the 2's, the first equation is that x equals lambda x, which means either x equals 0 or lambda equals 1. Now, it's very, very often the case that you get sort of 2 possibilities or even 3. You'll be able to factor these things. So you kind of need to take separate cases and lay out your logic very, very carefully. So let's just pick one of these cases. Let's, well, I guess we could also write down the other ones first. The second equation says that y is lambda times 2y after cancelling out that factor of 2. So here, we either have y equals 0 or lambda is 1/2. That's a possibility. And then finally, the last equation says that 2z minus 2 is minus lambda, which doesn't really tell us anything. It just relates lambda and z. So what we've got then, and we're going to have to come back to the other equations, so we might as well break these down into cases. Clearly, you cannot have lambda equals 1 and lambda equals 1/2. So we have possibility 1. Okay, let's suppose we try lambda equals 1. In that case, the second equation, so if lambda equals 1, you cannot have lambda equals 1/2. So we must have y equals 0. And also, in this equation, we have 2z minus 2 equals negative 1. But we don't know anything about x because the first equation just says x equals x. So we have y equals 0, we have 2z minus 2 equals minus 1. Well, let's simplify this. 2z minus 4 equals minus 1. Add 4 to both sides and divide by 2, and you see z is 3 halves. All right, so y equals 0, z equals 3 halves. What's x? Well, we use the constraint equation. So it's x squared plus 2y squared minus z equals 0. X we don't know. Y is 0. And z is 3 halves. So x is plus or minus root 3 over 2. So we've actually found, in this case, we found x, y, and z. And lambda, but who cares? So x is root 3 over 2, the square root of 3 over 2, or minus that quantity. Y is 0 and z is 3 halves. We better find out what f is. So f, in this case, plus or minus root 3 over 2, comma 0, comma 3 halves. And we plug this into x squared plus y squared plus z minus 2 all squared, and you find it's plus or minus root 3 over 2 all squared plus 0 squared plus 3 halves minus 2 all squared. This is 1/2 squared. This is 3 halves. And the answer is that's 6 quarters plus 1 quarter is 7 quarters. Okay, so at that critical like point, the value is 7 quarters. This is at the point, either of these points actually. There's 2 points which give you this value. We don't know if it's a maximum or a minimum, but we haven't finished yet. So we have to now do case 2. So if lambda is not 1, the other possibility is that x equals 0. Well, I guess then we move to the second equation, which says that either y equals 0 or lambda is 1/2. Well, let's try lambda equals 1/2. We can also, we'll have a third case as well, apparently. So in this case, y need not be 0, x is 0, but we come over to here and we find that 2z minus 2 equals minus lambda, which is minus 1/2. And we have to solve for z again, so this becomes a little bit repetitious. Again, this is 2z minus 4 is minus 1/2. We have to add 4 to both sides, and you actually get 3.5, which is 7 halves. And so z turns out to be 7 quarters. And we already know x equals 0, so now we have to find out what y is. So we go back to the constraint equation. We plug in x we know is 0, y is the unknown. Subtract z is 7/4, and you see that y squared should be 7/8. So y is plus or minus root 7/8. And to complete the case, we need to find f again. So I'll just sort of cram it in here because I have a little space. F of 0 plus or minus root 7/8, and z is 7/8. No, z is 7/4. Equals 0 squared plus root 7/8 squared is 7/8 plus 7/4 minus 2 all squared. That's the equation for f. 7/4 minus 2 is a quarter. So you've got 7/8 plus a 16th. So this is 15/16. Okay, that seems to be smaller than 7/4. And so this, so far, this is the maximum and this is the minimum. We've done the case lambda equals 1. We've done the case lambda equals 1/2. Over here, if neither 1 nor 1/2 are the value of lambda, we must have x and y equals 0. Both of them must be 0. So that's case 3, is that x equals 0 and y equals 0, and to hell with lambda. Well, that's okay, because we know from the constraint equation x squared plus 2y squared minus z squared is equal to, minus z rather, is equal to 0. If x and y is both 0, then z is 0 as well. Just plug it in there. And f at the origin is 0 squared plus 0 squared plus 0 minus 2 all squared, which is equal to 4. Okay, so we actually have 3 candidates, but if you look at it closely, it's 5 candidates because some of them have plus or minuses. So I'm going to line up the candidates. From case 1, we found the potential candidates were root 3 over 2, 0, 3 over 2, and minus root 3 over 2, 0, 3 over 2. From case 2, we had 0, root 7/8, and z was 7/4. And the same with the minus. And the last case was 0, 0, 0. Now, the maximum value here, or the value when we substituted in, was 3/2 in both cases. Here the value, this is the value of f. And here it was 7, what was it, 15/16. And here it was 4. All right, so what do we make of this? What's the smallest and what's the largest? What's the boundary? What's the boundary? What does this thing look like? What does the constraint look like? Yes?
I think the value of the first one should be 7/4.
Should be 7/4. Did I miscopy it? Yes, I did miscopy it. Thank you. F is 7/4. It's hard to see all the way over there. That makes a difference. Okay, so my question is, what then does the surface of constraint even look like? What does z equals x squared plus 2y squared look like? Anyone know? Yeah. Not a cone. Paraboloid, right. So if we actually draw z equals x squared plus 2y squared, this is one of the reasons we spent so long drawing these damn things. It looks like a paraboloid, like this, elliptical paraboloid. Here's 2, and the problem is saying which are the points on this paraboloid that are closest to 0, 0, 2, and which ones are furthest away. So there's no boundary, you see here, meaning we can pick any points on this paraboloid. I think if you think about the geometry of it, you'll see that you can pick some points which are pretty bloody far away. Just go way, way up this cone, not the cone, sorry, paraboloid, go way, way up and you'll get pretty far away. So actually, to hell with the Lagrange multipliers, you can just see from the geometry as you go, so there cannot be a maximum distance. Since x, y, z can be arbitrarily far from 0, 0, 2. If you want to be more precise about it, you can say there are solutions with z being very large, i.e. z can go to infinity is possible. Just pick really large values for x and y, and z can be as large as you like. Therefore, z minus 2 all squared can be huge, and the same thing with x squared plus y squared. This can happen for certain paths as you move away. However, we have found the minimum. We have found the minimum. What is the minimum? The minimum value is the smallest of these 3 numbers, which is this one. So the minimum square of distance is 15/16. So the min distance is the square root. Finally, I take the square root. And if you needed to say where it would occur, it's at either of these 2 points here. Okay, while you digest that, I'll just make sure that that agrees with the answer. If I can find it. I think I worked it out on the back somewhere. Aha, here it is. Yes, it agrees with the answer. There you go. No max, and the closest is 15/16. Woohoo! I'm sorry?
What is the 4 signify?
Okay, so the question is, why do you find a 4? Well, that's actually a local max. That's like a local max. See, here's the point that you're interested in. That distance is 4. It could be a local min as well. It's sort of hard to tell, but I think that if you look at points near it, it looks like this is a local max. But it is not the global max. And I don't know if your name's Max, by the way, but I'm using max as a short for maximum. I just thought I would point that out. Want some Pepsi, Max? Okay. So yeah, basically you can get these local maxima and minima just like you can for critical points, and so you have to actually check the values of the thing. So in this case, it would be very tempting to say that 4 is the answer, and without doing the geometry, you would fall into this trap, and you'd probably get still 8 out of 10, or whatever it's out of, for, let's see, it was out of 10, right? You'd probably get 8 out of 10 if you did all this work and then said that this is the local, this is the absolute minimum, and this is the absolute maximum. But you couldn't get the last 2 points because you would have missed the fact that the boundary is infinite in extent. Another question. What if you had switched the constraint is the question. As in, what if you got them the wrong way around? Well, as you can see, this equation here, or these 3, it doesn't really matter which way you put the lambda. You could put the lambda in front of the f, as long as you did it the same for all 3. But if you then set f to be equal to 0 instead of g, you would have a big problem. And the reason you'd have a problem, especially in this case, is that the only solution to f equals 0 is 0, 0, 2, because it's a sum of squares. So the problem becomes meaningless. So you've got to get the constraint, you've got to get the right function for the constraint. Another question up here. How did I choose which one was the constraint? Well, the problem said find all the points on z equals x squared plus 2y squared that minimize the distance. So I looked at it. There's only one equation you get out of that, which if you plug it, if you throw it all on the left-hand side, you get x squared plus 2y squared minus z equals 0. A constraint is an equation, not a function. It's actually an equation. If you don't happen to know it's something equals 0, or something equals something else, and rearrange it to say something equals 0, that's a constraint. Okay, if it says minimize or maximize f equals something, that's not a constraint because it's not an equation, it's just a function. So that's an easy way to tell. The constraint has to be an equation. Another question. The question is, yeah, it doesn't matter which side you put the lambda on. Sure, you could get rid of these lambdas here and put them all here, and the thing works just fine. However, be careful, if you put some of the lambdas here and some of them there, you will completely get mixed up. But I like it this way. I mean, this is the way I always do it because, I have the constraint. Now, I like to put it in front of the constraint derivatives, is what I'm saying. And part of the reason is actually my next little mini topic, which is sometimes there are 2 constraints. And then you really want the multipliers outside the constraints, otherwise it sort of gets confusing. So this is why I just like to do it this way. But yeah, it doesn't really matter as long as you are consistent. Are there any other questions about this example? Yes, thank you.
So, if on an exam question we got a question that was obviously meant to use Lagrange multiplier, you saw some other way to find the minimum. Like, for example, in this problem, you can just look at the geometry first and see that it would have to be like the cross section through the ellipse on the minor axis. You know what I mean? You can reduce it to just one variable.
Okay, so
Or 2 variables.
the question has a couple of ramifications, so just repeating it in a way for the benefit of everyone. Do you have to use Lagrange multipliers, for example, for a problem like this? Well, if the problem says use Lagrange multipliers, as it does in this case, then the answer is yes, you must use Lagrange multipliers, okay? Otherwise you shouldn't get full credit, or maybe even partial credit. If the problem just says find the maximum and minimum, you can use any legitimate way to do it. Okay, so maybe there's a way that avoids Lagrange multipliers. In this case, if the problem said simply find the maximum distance if it exists, then you don't need Lagrange multipliers. The geometry shows you what the maximum is, that in particular it doesn't have a maximum. So then it would be a waste of time to do all Lagrange multipliers. As it happens, it says find the closest points as well. Now you have to use Lagrange multipliers in some sense. So you have said reduce it to one. Okay, so maybe you can avoid, you're saying, well, look, we know that actually the thing is longer in this direction than it is in, so it's longer in the x direction, whatever that is, let's say here, than in the y direction. So it actually should be skinnier. So it kind of has to lie with x equals 0. So you're just sort of using some geometry to say, well, we need x equals 0, and then you've reduced it to a one, well, it's really a two variable. You could still use Lagrange multipliers for that. Two variable problem, or you could try to reduce that to one variable and do it that way. That would be fine if you explain yourself and the problem hadn't said use Lagrange multipliers. Okay, so, you know, I'm all for saving time, and as you see, it took a while, but, you know, these problems take a while, they're worth a lot of points. So try not to get too clever, because occasionally these things do trick you. But yeah, I'm all for alternative methods as long as you're clear. Just beware, if you ever use an alternative method and try to get fancy, if you're correct, if you don't explain yourself correctly, the grader may not realize what you're doing. And so you should always be very clear. Write sentences, don't just try to leave it up to the grader's imagination. There's a lot of papers to grade, there's a lot of people here, and it's very tempting to just sort of say, oh, I don't know what they're doing, and just go on. So beware. All right, any other problems about this example? Any other questions? No? Well, let's just talk about the two constraint version. I'm not going to do any more examples apart from one of this other sort, because I'm sure, as I said, there will be others coming up, and they do take quite a while, and I really want to get onto that summary. Here is the two constraint version that I was just talking about. Okay, so in this scenario, you still want to find the max or the min of some function f. Again, it's not an equation, it's just a function. But this time you might have two constraints. Which, by rearranging, again, put everything on one side, will look something like this. G of x, y, z, 0, and h of x, y, z equals 0. So instead of finding all the points on some surface, we're really finding all the points on the intersection of two surfaces, which is generally some sort of curve, and you want to find the minimum value of f just for points on that curve. So the method is very similar, except that you have two constraint equations and you have two multipliers. You have two multipliers. So here, the equations basically look like the grad of f. You need lambda times the grad of g plus mu. That's another Greek letter, another multiplier. Grad h. And again, you have g is 0 and h is 0. So there's actually now 5 equations. Again, I could write this out. I'll write out one sample. fx, well, fx is lambda gx plus mu hx, and etc. for y and z. So there's 3 equations there. So there's a total of 5 equations, but 5 unknowns. We still have 3, which are x, y, and z, but we have mu and lambda. So we have 2 extra auxiliary variables. Again, this is 3 equations. Whoops, this is 3 equations in one. Then one is written out in full. All right, so it's a very similar method. Still have to check boundary points and all that, yada yada. But let's look at an example of this. I'm all over the place now. Anyone have an example with 2 constraints? There's definitely one in here which I wanted to do, but here it is. Maybe someone brought one that's different from the one I was going to do. No? All right, well, I'll just do this one. All right, so the deal is this. We have two surfaces. S1, which looks like x squared plus y squared plus z squared minus 4x plus 1 equals 0. And S2, which is y squared minus x plus 1 equals 0. So there's two surfaces. The first part asks to sketch it, and the second part and third parts basically say maximize and minimize the distance to the origin. So find the max and min distance from points on both surfaces, distance from the origin. Okay, I'm sort of summarizing the three-part question all in one go, but that's it. All right, but I really like the first part, which instructs you. You want to hear that beep? Is that coming from your microphone now? You can hear me okay? Okay. Soon I'll just lose my voice altogether. All right. So we better do the first part, which is to sketch surfaces so we even have an idea of what the boundary is, if any. Now, these things don't erase quite as well as in fine 314, but what can you do? All right. Let's look at S1. What we really want to do is complete the square in x. So we have x squared minus 4x plus 4 is what we really should add to both sides. So we'll have x squared minus 4x plus 4. We'll leave the y squared and the z squared alone. We still have a plus 1. We just added 4 to both sides. That's my way of completing the square there. So rearranging a little bit, you get x minus 2 all squared plus y squared plus z squared equals 3. So this is a sphere. Not even an ellipsoid, because all the coefficients are 1. This is a sphere of radius root 3. And center 2, 0, 0. Well, let's do the x-axis here. Root 3 is a little less than 2. All right. Now, we also have to find the other surface, which is over here. That's a bit simpler. Y squared minus x plus 1 equals 0. Imagine you sketch that as just a regular old function in the xy plane. Y squared equals x minus 1. Well, that's a parabola with center at 1, 0, but tipped over because it's not y equals x squared, it's y squared equals this. So it's going to look like this. So what does it mean when there's no z dependence? The answer is it's a cylinder. It's basically take that and literally, if z-axis is coming out of the board, literally the parabola just comes in and out of the board, just straight out, perpendicular. But if you wanted to try to render it on the same sort of axes, with this being the x and the y, you kind of got to first of all realize that this is the positive x here, so it's kind of positive x corresponds to this direction, so you kind of got to draw it like this through x1, and then it'll just be a cylinder with cross sections, just this parabola. So that's that surface. What we're looking for is the intersection of these two surfaces, whatever that looks like. And there will be an intersection somehow, because this goes through 1, whereas this goes through 2 minus root 3, and you find that that's a little bit less than 1. What is the boundary of the intersection curve going to be? Is it going to be unbounded or is it going to be bounded? First of all, that's my question. I'll make it interactive. We're looking at the intersection of this sphere with this cylinder, and it's going to be some sort of curve. And my question is the curve bounded or unbounded? Bounded. Why is it bounded? Because it lies on the sphere and the sphere is bounded. Okay? It may or may not be closed. That could be a little tricky thing, right? A curve could actually have ends. But in this case, it's hard to see where the ends would be. The curve's got to be a closed curve on the sphere. So I don't want to get into that. That's sort of more of an intuitive thing. You can actually find the equation of that if you want to and verify that. Anyway, never mind this. Let's whip out the Lagrange multipliers. We have two constraints which correspond to these equations of the surfaces. And we're interested in minimizing or maximizing the distance from a point to the origin. So what is the function that we're going to care about? Again, let it be the square of the distance. So let f be the square of the distance to origin, i.e. f of x, y, z equals x squared plus y squared plus z squared. None of the z minus 2 in this case, just z squared. And the constraints are exactly the equations of the surfaces. And I'll just leave it in the original form. X squared plus y squared plus z squared minus 4x plus 1. And that has to equal 0. And then h of x, y, z has got to be the other equation, which is y squared minus x plus 1, and that has to equal 0. So it's a two-constraint Lagrange multiplier problem. Let's do it. So first of all, we're going to need fx. So that's just 2x. Fy, 2z. Gx is 2x minus 4. Gy is 2y. Gz is 2z, so I just differentiated that. Hx is minus 1. Hy is 2y. And hz is 0. We've got these three equations here. We have fx equals lambda gx plus mu hx. So that equation becomes 2x is lambda 2x minus 4. Maybe I'll turn it down a little bit. I think it got turned up while I was fiddling around with it, it seems. At the risk of jinxing it, how's that? Can you still hear me? Yes? Louder? Softer? Perfect? Okay, good. What? Yes. I'm going to put this in. Thank you. All right, so that's the x equation. The y equation, similarly, we have to just plug these things in. We get 2y is lambda times 2y plus mu times 2y. All those derivatives are 2y, because they were all y squareds. And finally, the z equation, again, you pack these things together, and you get 2z is lambda 2z. And there's no mu there, because the z derivative is 0. Z doesn't enter into the equation for h, the second constraint. All right, so we have to solve these along with the two constraint equations, which I'll write again. X squared plus y squared plus z squared minus 4x plus 1 equals 0, and y squared minus x plus 1 equals 0. So 5 equations, 5 unknowns. Now here comes an orgy of solving. We have 2z is lambda 2z. I sort of gravitate to that one because it's the simplest. That's the simplest. So from there, it's easy to see that either z is 0 or lambda is 1. So these are the two cases. We find a similar sort of thing that we found before. Let us take a case 1 to be lambda equals 1, and we'll come back for the other one. If lambda equals 1, we now go back to the first two equations, and then we'll have 2x equals 2x minus 4 minus mu. Well, that's not so bad. 2x's cancel, and this would mean mu is negative 4. Well, we better check the second equation and see if it's consistent. We have 2y equals lambda is 1 again, 2y plus mu times 2y. Well, 2y's cancel. We know mu is negative 4, so that's not actually 0. So since mu is minus 4, we must then have y equals 0. That's the only way you can have 2 mu y being equal to 0 with mu being negative 4. So when lambda equals 1, x could be anything, but y must be 0. Okay? So that's what we found. Now we've got to go back to the constraint equations and see what we can say about x and z. The second constraint equation here has only y and x in it, so let's look at that one. We have y squared minus x plus 1 equals 0, but y is 0. So x is 1. Then we go to the other constraint equation, x squared plus y squared, I'll just write it out again, plus z squared minus 4x plus 1 equals 0. And we're going to plug in y equals 0 and x equals 1. We'll get 1 plus 0 plus z squared minus 4 plus 1 equals 0. And if you work this out, then you get z squared is 2. So z is plus minus 2, square root of 2. All right, so moving over here, the points that we found from this case are 1, 0, and plus or minus 2. In each case, the square of the distance, f is the sum of the squares, so it's 1 squared plus 0 squared plus or minus root 2 all squared, and this works out to be 3. So the square of the distance is 3 in this case. All right. However, that was case 1. Maybe it's a good idea to write case 1 and then case 2. And bear in mind there might be more, so case 2 or more. But that way we'll remember to come back and sort of go back to the equations and try the other case. It's very easy to forget after doing all that extra work. So my advice is write it down earlier that you're going to need to do it and then check them off. Maybe we should even go back and put a check mark once we've done case 1. Okay, so case 2, we started with this equation that 2z is lambda 2z, and we tried lambda equals 1. The other possibility is that z equals 0, and we don't know what lambda is. Lambda equals anything. At least anything so far. Well, if that's the case, then we can come back to the other two equations. So this is going to get a little bit messier. We'll come back to the first equation, 2x. Let's expand it out a little bit. We're going to have lambda 2x minus 4 lambda minus mu. And we'll also have 2y is lambda 2y plus mu 2y. And then we also have, well, okay, before we also have, look at this equation. I gravitate towards this equation because I've noticed something. Y is a factor. So I have either y equals 0 Or we can divide by y, and we'll get 2. Actually, we can divide by 2 anyway. So, or we can divide by y, in which case you'll get 1 equals lambda plus mu. So, unfortunately, we now have a case 2a and case 2b. So, this will be case 2a, which shouldn't be too bad, and this will be case 2b. See, these problems are quite involved. However, case 2a is pretty nice. It's pretty nice. In case 2a, we already know that z equals 0, and we've assumed that y equals 0. So what on earth could x be? Well, according to the second equation, y squared minus x plus 1 equals 0. So again, x must be 1. But if we plug this into the first constraint, we find that that doesn't work. But 1, 0, 0 is not on S1. i.e. it doesn't satisfy this first constraint, x squared plus y squared plus z squared minus 4x plus 1 equals 0. If you plug it in, you'll see it's not. Okay, it's not on the sphere. So this is no good. No solution here. So we're really in the proper case here where lambda plus mu equals 1. In other words, we can write mu is... So mu is 1 minus lambda. Okay, let's go back to the first equation now and replace mu by 1 minus lambda. So now we're going to put that back here. It's like a rabbit warren, you know, this thing keeps just getting deeper and deeper. So we have 2x is lambda times 2x minus 4 lambda minus mu, which is 1 minus lambda. And so if you rearrange a little bit, you get 2x is lambda times 2x, and this is going to be minus 4 lambda plus a lambda, so it's minus 3 lambda minus 1. So that's an equation. Now, we don't know what y is at all. However, we do have an equation. So this is now our new equation that doesn't have lambda, that doesn't have mu in it. Okay? So we can now go back to the other equation here. We know z equals 0. So the first constraint equation becomes x squared plus y squared. Z is 0. So minus 4x plus 1 equals 0. So I'll call that equation 2 for the moment. And then the other equation is still y squared minus x plus 1 equals 0. So I now have 3 unknowns. I've gotten rid of the mu. Z happens to be 0. And everything has reduced to solving these 3 equations here. So it's a little bit of a mess. But maybe we can unravel something. Actually, the lambda equation here seems a little bit bizarre in that there's no lambda anywhere else. So if we come back over here, we'll see z equals 0, no problem. This equation with y not equal to 0, it just related lambda and mu. So actually, this equation is worthless. Doesn't really say anything. It will allow us to find lambda, but who cares? We don't need to find lambda. So actually, we just need to solve these 2 equations together, and that is a legitimate solution. So that's with z equals 0. So if we do this, what do we find? Well, we have y squared equals x minus 1. So we'll plug that in here instead. And we will get x squared plus x minus 1 minus 4x plus 1 equals 0. In other words, x squared minus 3x and the minus 1 and plus 1 cancel out. And so you get or x equals 3. If x equals 0, y squared equals x minus 1, which is minus 1. That's no good. No solution. But if x equals 3, y squared is 3 minus 1, which is 2, So y is plus or minus the square root of 2. And so we found z is 0, we found y is plus or minus the square root of 2, and x equals 3. So the points we care about is this: f of 3 plus or minus root 2 is 0. And that is 3 squared plus or minus root 2 squared plus 0 squared. 3 squared is 9, root 2, 11. There's no more cases. We've exhausted every possibility of solving these equations. In one case, we found 2 points that gave a distance of 3. In the other case, we found 2 points that both of which have a distance of 11. There's no boundary points, as we've discovered that the curve is bounded. So basically, one must be the maximum, one must be the minimum. This is the maximum, this is the minimum. But the correct solution involves writing out a sentence, which I propose to dictate, because otherwise my arm will drop off eventually. So here is the sentence. The maximum distance is root 11, which occurs at the points 3, plus or minus root 2, 0. This. The minimum distance is root 3, rather. Square root of 3, which occurs at these points, 1, 0, plus or minus root 2. Now let's see if that's right. Yep, that's what it says. No, it's not. Yes, it is. Sorry. Okay, question up here. So how do you know you've gotten all the points? Well, the question is, what does the actual intersection look like? Maybe the time has come to draw the intersection. You've somehow got to wedge a sphere in here. So the actual intersection is going to be some curve that looks like this. I don't know exactly what the shape of it is without solving it. If you really want to, you just have to solve these two constraint equations together. It's not so bad. I mean, if you say this equals this, the y's cancel out, and you just have some curve in the x and z thing, and so which you can then solve and plug back into y. So it will be some curve that's some sort of ellipsy type of thing, which has no boundary. So those are the only possibilities. There's no boundary points to check. Okay, so again, the maxima and minima occur at the solutions to these Lagrange equations or on the boundary. And if there's no boundary, then those are the only 2 points to check. So what you write is no boundary. Therefore, these must be the max and the min. All right? What is the boundary? Well, if you have a surface, suppose the question was, find the minimum of some function on the circle or the sphere inside the sphere where x squared plus y squared plus z squared is less than or equal to, say, 4. Well, then the boundary would be x squared plus y squared plus z squared equals 4. Okay, so those would be the boundary points that you'd have to check. But in the two examples we've looked at, in the first case there was no boundary, but it went off to infinities. So the boundary was sort of out there. And in the second case, there is literally no boundary. The thing is a closed curve. So there's no boundary points. There's no edge of it. It's just a closed curve. All right? Another question.
Could you set those two constraint equations equal and then do it with one constraint?
Yeah, so of course another way of doing it is to try to find the intersection and then solve and find one constraint. And that would be another way of doing it, but it may be harder to do it that way. So you could reduce it to a one constraint problem, sure. Any other questions about this example? Well, another question. Okay, so the question is, once you see 2z is lambda 2z, why can you not cancel out the z? Well, you can, but not if it's 0. If z is 0, then both sides are 0 no matter what lambda is. And that's why I take a separate case. If you do just cancel out the z's willy-nilly, you will miss that other point. And you will be quite confused because you'll only find a 3, you won't find a maximum or a minimum. You won't know what it is, okay? So whenever you cancel out, make sure it's not 0. The thing that you're canceling cannot be 0. If it is, then you take a separate case to deal with that, as I did, all right? You can always cancel or z equals 0, but this is what I've said, z equals 0 or lambda equals 1. All right? If the z is 0, you can't cancel. If it is 0, if it's non-zero, you can cancel, and then you'll find lambda equals 1. Another question.
Going back to the
Yes.
if we're given a problem like that, what we should do is we should do Lagrange multipliers of whatever constraints we have without considering the sphere, and then do another one considering the sphere as a hollow sphere and figure out which of the points.
Oh, you mean this particular problem here?
Yeah.
Okay. So the question is, and I don't have time to do it now, but I'm sure there's a few in the previous finals, previous midterms, so I'm sure they'll come up. If the question is just to find a regular minimum, suppose the question was find the minimum of some function, or the maximum of some function on this sphere here, right?
My question was, are we going to get a question, I mean, we may not get this question, but if we're trying to find, for example, the minimum on a surface, not the minimum on a surface, the minimum distance between a surface and a point,
Yes.
and the maximum distance between a surface and a point within a defined area.
Yeah, then you have to, okay. There's two things. I want to complete my thought first, and then I'll come back to your problem. Okay, so this is important. I suspect, but I'm running way behind, and I'm sorry. What can I do? Suppose for a separate problem, you wanted to minimize a function f on this sphere, x squared plus y squared plus z squared less than or equal to 4. So it's the boundary and the interior of the sphere. What you would do is find the critical points of the function inside the sphere and check their values. But then you have to check also the boundary values. Now the boundary is actually x squared plus y squared plus z squared equals 4. And that's a Lagrange multiplier problem. You'll have a function f, and you want to maximize it or minimize it subject to that constraint. So the boundary becomes a Lagrange multiplier problem without any boundary, because the sphere itself has no boundary. The sphere and its interior, as in the closed sphere, this solid object, the boundary is the surface. But if you then consider just the surface, the boundary of that is nothing. There's no boundary of the surface, because there's no separation. If you're inside the sphere and you're walking around, you're like a little dust mite or something, and you get to the edge of the sphere, that's a clear boundary. But if you're just actually walking on the surface, there's no edge of it. You never fall off the surface. Columbus, for example. Compare Columbus to a dolphin. Columbus went along the surface of the earth and never fell off, whereas dolphins can leap out and back in, and they get wet or otherwise. Analogy master! All right. We still have to do Taylor series. Taylor series I propose to do on this 2 blackboards here. I propose to say very little about it. I'm not going to do everything or anything like that. I'm just going to show you what you really need to know for this exam, and it is as follows. You have some function. Okay, bear with me. I'm going to start the summary very short. You have some function f of 2 variables. I'm only going to worry about the 2 variable case. And you're interested in a quadratic approximation at the point x0, y0. Okay, so you kind of just need to know the formula for this. But the beauty of it is that it's very similar to the linearization formula that you already learnt. It's just got some extra junk. So here it is. I'll call it P2, even though the textbook doesn't. This is the Taylor polynomial of quadratic order, of order 2. Equals the value at x0, y0 plus the first derivative times x minus x0. That's the x derivative. Then you'll have a y derivative, always evaluated at that magic point. Now, if we just stopped here, this is the linearization that you're already supposed to know for linear approximations. Which we called L of xy. All the Taylor thing does is give you a second order correction which involves the second derivatives. And it looks like this. And we put a half because the single variable Taylor series involves a 1 over 2 factorial. So there's a half there. It's a little bit more complicated with the two variables. You'll have a second derivative with respect to x both times x minus x0 squared. You'll have a mixed partial with a 2 coefficient because effectively you have an xy and a yx. That's where the 2 comes from. And then you have a quadratic term which is mixed. And then finally, still within the parentheses, you have the y derivative, double derivative, second derivative, times the quadratic in y. Okay, so it seems a little bit ugly, but as you see, I was just able to pull it out of wherever, thin air. I guess I've been doing this a little longer than you, but still, it's a formula that makes sense if you think about it. You've got to see the patterns in it and where they come from, right? Second derivative, square in x. Mixed second derivative, x times y. Y derivatives, y squared. And it's always y minus y0 or x minus x0. It's effectively a translation to the point x0, y0, or from there to the origin. So if you know this, then in the rare event that you actually get asked to find a quadratic approximation, you can do it. So here's an example. Suppose f of xy is defined to be log, natural log of 2x plus y plus 1. And we would like the expansion at the origin. Find the second order Taylor at the origin. Okay, so this is not a quadratic function. We want to find a quadratic function that closely approximates it. Well, we're going to have to find all these derivatives. So we need the first derivatives and the second derivatives. So there's 5 of them. fx, just differentiate with respect to x. You'll get 2 over 2x plus y plus 1. If y, you just get 1 over 2x plus y plus 1. How about the second derivatives? Well, differentiate this. The derivative of 1 over x is negative 1 over x squared. This coefficient of 2 here comes out the top, though, and you get negative 4 over 2x plus y plus 1 all squared. To find fxy, you can either differentiate this with respect to y or this with respect to x. It's up to you. In fact, you can do them both and check that you get the same answer. In either case, if you differentiate that with respect to y, then you just get a 2 still on the top, and you'll get negative 2 over 2x plus y plus 1 all squared. And finally, differentiating this with respect to y gives you fyy. Okay, I'm not going to fit it on this panel. Sorry, it'll fit just up there. All right, so you get negative 1 over 2x plus y plus 1 all squared. So that's what some derivatives. Now, in order to apply the formula, we have to evaluate those derivatives and the function itself at the origin. So, because the origin is the point that we are told we are interested in. So now, you plug in x equals y equals 0. into f, fx, fy, fxx, fxy, fyy. Okay? If you plug in over here 0, 0, you get log 1. So that's 0. And then it's easy to see what the others are. The denominators are always 1 in every case. So so here, f equals 0, fx equals 2, fy equals 1, fxx equals negative 4, fxy equals negative 2, fyy equals negative 1. So I just took those 6 equations that are on that left board and plugged in x equals y equals 0. And now I just have the formula. P2 of xy equals the value at 0 plus the x derivative times x minus 0 plus the y derivative times y minus 0 plus, that's the linearization, plus 1/2 second x derivative x minus 0 all squared plus 2 times, the 2 is in the formula, I now need the second mixed derivative, x minus 0, y minus 0, and finally the y derivative these zeros because I just want to emphasize that it's around 0, 0. But now I'm just going to sort of write it as 2x plus y. 1/2 times minus 4 is minus 2, x squared. Minus 4, but then we have a half again, so it's minus 2xy. And then minus 1, don't forget the half, so it's minus 1/2 y squared. And there's a quadratic that approximates this. And so if we had to find an approximate value of f of, say, 0.1 comma minus 0.2, then you just plug it in, and it's probably a bit messy, but you could just calculate P2. Since this point is near the origin, you just plug this into here and you'd see it's 2 times 0.1 plus etc. Okay? So the point is that the answer that you get is a good approximation to the original function when you're near the point 0, 0. It's a perfect approximation when you're at the point 0, 0. All right, so that's all I really need to say about Taylor series. I mean, there's this whole theory. You can do it in 3 variables instead of 2. You can do it to cubic order. You can estimate the errors. It deserves a lot more time than we have to give it. But the likelihood of getting any other sort of question on the midterm seems pretty remote. So I'm not going to touch it now. If we want to talk about it later, we can do it. We do have a question. Yeah, look, you know, the error, you can say it's less than the next term, but you have to replace the derivatives by the maximum possible values of the derivatives. Then you get the correct estimate for the error. But that's, as I say, I mean, I've never seen a midterm question on it. If anyone produces a question, we can do it in the Q&A session. But I don't want to talk about the error. I think it's, as I say, exceedingly unlikely that you'd need to use a cubic error term to estimate this in the midterm. I mean, it's possible. It's technically in the course, but I'd rather go into the summary. Unless there are any other questions about this before I jump ahead. All right, geometry. Limits. Derivatives. Max min. Good news is, I've almost done all of 4 already. But we have to go and do the summary of the first 3. That is. All right. So here's what I think you need to know about geometry. That, I think, classifies into two areas. Vectors, surface graphs. Okay, so take A first. Here are all the things I think you need to know how to deal with vectors. I'm not going to give examples of all these things. I just do not have time. All right? So, first of all, you need to know how to find the length of a vector and how to make it into a unit vector. By dividing by its length. So again, the length of x, y, z is the square root of x squared plus y squared plus z squared. Of course, there's 2D and 3D versions of all of these. Very rarely is there any difference between the 2 and the 3 except for the extra variable. Okay, so you need to know how to find the length. You need to know how to take the dot product of u dot v. You all know the formula for that, so I'm not going to write it out. However, not a bad idea to know this, which may come up. V dot v is the same thing as the length of v squared. That's a good equation to learn in this context. After all, v dot v is the sum of the squares of the coordinates, x squared plus y squared plus z squared. That's the same as the length. Is that the microphone? What do you think? Is it still on? Ah, failing me. Maybe I'll fail you. No, just kidding. Just kidding. I can't do that any more than I could give you an A+. All right. Next. Angle between two vectors. You need to know, given two vectors, you need to know how to take the angle. It comes from the formula, which you should know. U dot v is the length of u times the length of v times cosine theta, where theta is the angle of two vectors, angle between the two vectors. This means that cosine theta is u dot v over the product of the lengths. So that's the formula you need for the angle between two vectors. No one's going to tell this to you. The formula's not on the paper. You're not allowed to bring it in. You just have to know it. I learn this, and then I can derive that. All right. Occasionally, you might need to know the projection. I'll do projection of u onto v just to be consistent. Okay, so first of all, what does it mean? You need to know the geometry of it. Here's a vector v. Here's the vector u. The projection, you drop the perpendicular. This is the projection. So it's a scalar multiple of v, the thing that you're projecting onto. You just have to adjust the length to get it right. And you ought to know that the formula is u dot v. I like to remember it as u dot v over v dot v times v. And you can also replace the bottom by the length of v squared, which is the way it is on the textbook. But to me, it's a little sort of more symmetric to go u dot v over v dot v times v. I remember there's lots of v's. There's only one u. And there's some dots. I'm sure you're all very good at memorizing things by now. Unfortunately, there's quite a few formulas to memorize, but again, like most of math, if you understand what's going on, then the memory is not a huge part of this. Really, it's the understanding. All right. You need to know the cross product. So, obviously, by now, this formula is second nature to you. This tells you the cross product of these two vectors. E is not exponential, it's just a variable here. Okay, so you need to know that form, that's the computational version in coordinates, but you also need to know the geometry of it. It's a little bit complicated. If you want to know something about U cross V, it's a vector first of all. So it's a vector which is normal. So I'm going to call it alpha n. So it's a vector, as I say, n is normal to U and V. Or perpendicular, if you prefer, to U and V, subject to the right-hand rule. So if you really need to know what it is, my version of the right-hand rule is to point the thumb, which is 1, along the first vector, say U, 2 along the second vector V, and then 3 will stick out in the correct normal direction. So if this is U and this is V, then it's going to go down. Of course, it might be sideways or whatever. And try not to dislocate your fingers, please, during this exam. It has happened. Not at this university. But it's actually quite fun to watch people in physics and math exams like this, doing like this. There's also another version that's less physically rigorous involving this, but I think it's less reliable. So go the injury and do it, get the question right. That's my priority. All right. Now, what is the alpha? The alpha is the magnitude of this, and that is U, the length of U, the length of V, sine theta. It's the length of U, length of V, sine theta. It's not, the dot product is UV cosine theta, but that's all there is to the story, because the answer of the dot product is a scalar. The cross product, the answer is a vector whose length is UV sine theta, length U, length V, sine theta, but it also has this unit normal thing, so I should say unit normal. So it's a little bit more complicated. That's just the way it is. I don't get into the philosophy of the night before the midterm. Okay, still continuing with the geometry. Vector stuff from earlier on. But notice how we ended up using it a lot when we took directional derivatives and all this other stuff. So it wasn't just isolated. The area of a triangle spanned by U and V. So if you want the area of this triangle, it's 1/2 U V sine theta, just by the standard geometry. This is the length of the cross product times 1/2. So that is, so find U cross V, take the length, and remember that means you have to take the sum of the squares of the coordinates and take the square root at the end, and then multiply by 1/2, and you get the area. Okay, it's very easy, but in the heat of the exam, you might find that you take the cross product, and you get some vector, and you say, well, what's the area? Take the length. Okay, this you need to know. All right, triple box product. You have 3 vectors, U, V, and W. And to be consistent, I'll let U be A, B, C, V be D, E, F, and W be G, H, J. I can't bring myself to use I. So the triple box product is pretty resistant to the way that you write it. You can write it as U dot V cross W, or U cross V dot W. You have to dot 2 vectors, so you cannot write U dot V cross W like this. This doesn't make sense, because U dot V is a scalar, and you can't cross a scalar with a vector. But this is a vector, and you can dot a vector and a vector. So the point is, it doesn't really matter which order you do it in as long as it makes sense. But if you do switch two of them around, then the sign changes. In any case, this you find in a very similar way. You just write out the coordinates. It's like the cross product, but it's not a vector. This j is not the standard sort of j either. I didn't put a line underneath it, so I kind of escape. So you get, this is a scalar. It's also known as the scalar triple product, and it represents the volume. So this equals the volume of the parallelepiped, which basically is a fancy name for a squished box. So you go whoop, 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 whoop. So it's the volume of that. If the three vectors lie in the same plane, then it will be 0. All right, so those are the basic vector things. Now let's talk about lines. Okay, equation of a line. You need to know not only sort of how to find it, but you need to know what you're looking for. An equation of the line basically has a parameter. It's different from an equation of a plane. It always looks like this. R of t, and the parameter doesn't have to be t, but whatever. It's going to be some vector, say, u plus tv. And what does this mean? Well, u is some point on the line, and v is the direction vector, and the line will actually be this. So, in fact, u is any point on the line. And when I say point, I mean a vector joining, the point is here, the u is the vector joining 0, 0, 0 to that point. So I'm sort of interchanging vector and point. And v is any direction along the line. So there's no unique answer. You actually have a whole lot of choice. You can choose any point u on the line, and v can be any direction. It can be any multiple of the direction. It can be longer, it can be shorter, it can be backwards. It can't be 0. If it's the 0 vector, then you don't have a line, you just have a point. But in any case, I'm just trying to say that you have to even be able to recognize that unless there's a parameter, it's not really an equation of a line, it's probably a plane. So this is a kind of, this can trip you up. This is a sort of way it could trip you up. What is, in space, x, y, z, what does y equals 3 look like? What does y equals 3 look like? Make sure you can even answer that question. It looks like it should be a line, right? Because y equals 3, that's just like a horizontal line. It's actually a plane. That's a plane. Y, x, z, y equals 3 is the plane parallel to the xz plane of all the coordinates whose y, of all the points whose y coordinates are 3. All right? So just be careful. It doesn't have a parameter. It's probably a plane. Okay, that's a common mistake. All right. No, but if I say something that's not quite clear, please stop me. Okay, you need to be able to find the distance from a point to a line. A point, what do I call it? S to a line. So we have this point S and some line here, and the line is given by P. I'm going to call this now P. So P is a point on the line, and V is a vector. So P replaces the U that I had before. So the distance is very simple. All you do is you take the cross product of PS with the vector V. So this is the cross product. Take that length and divide by the length of V. Actually, I'll put... sorry? Okay, the reason this works is that the cross product, the length of this, is actually well, I don't want to get stuck on acute angles and obtuse angles. I'll just draw S out over here. PS cross V is this length times sine theta times the length of V, but I'm dividing by the length of V, so it'll just be actually this distance here, which is PS sine theta. That's the length that you want, and so the formula works. Again, it's nice to understand what you're doing, but it's also good to just remember the formula. Kind of helps at this stage. All right, so that's something that should be in your toolkit. Here's another thing that should be in your toolkit, which comes up all the time. Here it is. Important one. If you have a plane through x0, y0, z0 with normal n, doesn't have to be unit normal. Let's say normal A, B, C. It doesn't have to be a unit normal. This has the equation A, x minus x0 plus b, y minus y0 plus c, z minus z0 equals 0. Okay, so in that context, y equals 3. So we can reverse engineer it. If you have y equals 3 as the plane, you should think of this as 0x plus 1 y minus 3 plus 0z equals 0. See, I've just rearranged the 3 to be over there with the y, and I put a coefficient of 1 out of it. And now you can see that the plane goes through 0, 3, 0, but has normal 0, 1, 0. That's a normal. And you can see that that's consistent, that the normal is along the direction of y. Okay, so you kind of reverse it. If you have a plane, you can get a normal just by reading off the coefficients. Write that down. All right, the summary continues. Okay, how do you find the distance from a point to a plane? We've just found the distance from a point to a line. The distance, from point S to plane with normal, not necessarily unit normal. The good news is the formula is very simple, or very similar rather to this. It's just the dot product over the length of V. You do have to take the absolute value. Just as a little comment, this is actually a regular old absolute value because this is just a scalar. Here, this is a length. This is a length of a vector. So maybe I'll just okay, V is not V. V is N. Thank you. I was trying to be very close to the other formula, but that was kind of dumb. And P is a point on the plane. So P, as it was a point on the line, P is the point on the plane, N is a normal, not necessarily unit, and S is some point here. And by taking the dot product between PS and N, you effectively get the length of PS times the length of N. We divide by the length of N times cosine theta. And cosine is what you want because you're in between here and here. So this is the length you want, which is PS cosine theta. That's why it works. Okay, the other one needs to be a sine. You're taking the cross product with the tangent vector. It's the dot product with a normal vector. Since tangents and normals are orthogonal, one of them you need sine and one of them you need cosine. So it makes some sort of sense. But again, learn the formula. Thank you for pointing out the little VN confusion there. So plane with normal n and p a point in it. Point on the plane. All right. Let's continue, shall we? How about the line of intersection of two planes? So you have two planes. Most of the time, the two planes could be parallel, in which case they won't intersect. They could be the same plane, in which case they intersect everywhere on either of them. Or they intersect on a line. So 2 points usually intersect in a line. The best way to find that line, although not the only way, you can actually solve the equation simultaneously, but the snazzy way of doing it is that to find the line, what you do is you let V be equal to N1 cross N2, where these are the normals to the planes. And remember, if you have the equation for the plane, it's really easy to find the normal. You just read off the coefficients as a vector. So if you take the cross product, you get your V, which is a direction. So this gives you V. You also need a point. So then find a point on both planes. And the easy way to do that normally is to say set x equals 0 and solve for y and z. So you have two equations. You just need to find one point that satisfies both of them. So if you set x equals 0, you just have two equations in y and z. Sometimes that doesn't work and you need to set y equals 0 or z equals 0. But pretty much most of the time x equals 0, say, will work. Let's call that point u. So then the equation is r of t equals u plus tv, as it was before. So to find a line, you have to find a vector and a point. The point you kind of fudge around. The vector v that's along the line is just a good candidate, is just the cross product of the normals. All right, so that's the method there. Okay, just a couple more things before we talk about the surfaces. Actually, only one more thing. The angle between two planes, I've never seen a question on this in the midterm, but it's, by definition, all you have to do is find the angle between the normals. So you read off the normals, and you use the formula that I wrote up before, n1 dot n2 over the lengths, product of lengths. So I don't propose that you remember that formula separately. Just remember it's the angle between the normals, and remember how to find the angle between two vectors. All right? Okay, so that is part A of part 1. But we've already done part 4, and part 2 is not that long. Part 3 is pretty long. Okay, so make sure you can do all of that. You will find most of the questions on vectors fit into that. All right, surfaces. I don't want to spend long on surfaces because you've comparatively graphed these things till the cows come home. But I will give you a quick summary of what the situation is. Okay, so we'll take a break soonish. The first type is if one variable is missing. It's going to be a cylinder, not necessarily the normal cylinder, but sort of maybe like that parabolic cylinder we looked at earlier. You simply, and maybe you should write this down, graph the equation in the plane with the other variable missing, and then just cylindrize it by moving it up and down. So that's a very simple case. Otherwise, there's a quadric surface. If you have x squared plus y squared plus z squared, maybe with coefficients. Now, I could write a, b, and c, but I'm just going to put a squiggle. The main thing is that it's... main thing is that it's positive. If this is equal to some positive number, it's an ellipsoid. And the important thing is that they're all positive coefficients. 3 pluses. 3 positive coefficients. Okay, so that's sort of prototype number 1. If you have 2 positive coefficients and 1 negative coefficient, again, sorry? Something x squared plus something y squared plus something z squared equals some positive number. It's an ellipsoid. If it's 0, then it's just a point. And if it's negative, then it's nothing. So, I mean, that could be a good trick question, but most of the time, I've never seen that come up where they try to trick you like this. But basically, if it's something x squared plus something y squared minus something z squared, then there's 2 positives and 1 negative. And a lot depends on what's on the right-hand side. If this thing on the right-hand side is a 0, you get a cone, elliptical cone. So the cross sections are ellipsoids, not necessarily. It's a double cone. I should really draw these things, but we've seen this a lot. So, if it's positive, you get a hyperboloid of 1 sheet. That's this. I'll just draw the little mnemonic. And the ellipsoid. If it's negative, you get hyperboloid of 2 sheets. Again, the orientation depends on how you draw the axis and whether it's x, y, and z. I'll talk more about that in terms of variations. One thing I want to point out is that this is the only 2 possibilities. If 2 of them are negative and one's positive, multiply the equation by -1, and lo and behold, 2 of them will become positive. If they're all negative, then, gee, multiply by -1, they all become positive. But that's probably just a silly trick. All right, the only other possibility, as far as we're concerned, of the basic case, of the basic type, is where we have a linear term. So suppose we have something x squared plus something y squared, but then maybe we have minus z equals 0. Well, that's going to be an elliptical paraboloid of this sort. Not to be confused with one of the sheets here. That cross-section's a hyperbola, whereas this is a parabola. Very similar, but not quite the same. Hyperbolas have asymptotes. Parabolas don't. They just keep getting wider and wider. Now, what about this? Something x squared minus something y squared minus z. That is the hyperbolic paraboloid. And that's the one with the bloody saddle point. All right? Okay, so you sort of should be aware of these basic types, and what you're looking for is whether they're all squares, or maybe one of them's not a square, in which case it's the paraboloid. And if they are squares, then are they all the same sign, or is one different from the other 2? And if there is a linear, then are the squares the same sign, in which case it's elliptic paraboloid, otherwise it's got the saddle-y sort of thing. So this is the basic scenario. And then the modifications, first of all, I've left these spaces for coefficients. All the coefficients do is stretch and shrink things. So if you have a coefficient of, say, 4x squared, that actually squishes the x direction by a factor of 2. So whatever it was without it, it'll be squished by 2. Why is it squished? Because when you multiply by 4, the x can be a lot lazier. It can be a lot smaller for the same effect. And the reason it's 2 instead of 4 is because of the square. So it only pulls half of its weight because it only needs 2 because it's got this cushy 4 outside. It's a common mistake to stretch it by 2. But actually you've got to squish it because the 4 is doing the work for you. Of course, if it was a 1/4 x squared, then it would be stretched by a factor of 2. So that's one modification. Yeah, question?
For case 3, if you had a positive z, that would be
No. Well, okay. If you have, so the question is, what if you have positive z? If you have positive z in this case, paraboloid. And the same in the other case. You get the flipped over hyperboloid. It's actually, this case is sort of, you just switch x and y, and then that's the same as doing the opposite of z. So you don't get nothing because the z is not squared. Okay? So that's one modification. Another modification is sometimes you have to complete the square. If there are linear terms, if, for example, x squared minus 4x, like we saw, complete the square first. What that does is shift the axes around. If instead you have x minus 2 all squared, so linear term. If you have a linear term like, for example, x squared minus 4x comes up there, then you complete the square and you shift the picture over. And finally, just in the case of the paraboloid, if you don't have a 0 here but you have something else, suppose you have a 1. So the final example would be, suppose you have x squared plus y squared minus z equals 1. There's no completing the square, but you do want to do something like this. X squared plus y squared plus, minus z plus 1 equals 0. So I brought the 1 over to the left-hand side and factored it, and now you can see that that's just shifted the picture down by minus 1 on the z-axis. So it actually is a paraboloid there. If in doubt, you can always find the intercepts. This is not a bad idea, no matter what it is. Even if you recognize exactly what it is, you should still try to find the intercepts. And to do those, you do exactly what you would have done in the one variable thing. So always try to find the intercepts. Of course, sometimes there aren't intercepts. There's no z-intercept on that hyperboloid of one sheet, for example. But find intercepts. So to find the z-intercept, let x and y be 0 and solve, etc. And then finally, the only other thing I want to say about surfaces is, remember, a level surface, or curve, depending on how many variables, of f is the graph maybe there's no z if it's only 2 variables, equals c, where this is some constant. And for each c, a different level surface. Different level. So that's just a definition. It completely ties into what we've said, but it can be confusing. Now, one little example of this, which pertains to the hyperboloid case, is that if you look at, say, x squared plus y squared minus z squared equals c, it's worth knowing that the level surfaces are as follows. C equals 0. Well, let me just sketch them all on one thing. C equals 0 is this cone. actually a circular cone. So this is C equals 0, a cone. When C is positive, you get a hyperboloid of one sheet, as we've seen, that's asymptotic to the cone. I should have used different colors. What the hell? I'll use different colors. What the hell? So the cone can be in the white. So C greater than 0, whereas green will do. Looks very similar to the white. What else have I got? How about purple? Pink. That'll do. C less than 0, you get the two-sheet hyperboloid. Now, doesn't it depend on what C is? Yes. For different values of C, you get different nested versions of these things, but they're all still asymptotic to that cone. I didn't really show that very clearly, but they are asymptotic. And similarly, you get different bowls. In fact, for all the different values of C, you actually flesh out all of space. It's like carving, it's like peeling an onion, except that it's a really weird shaped onion with a cone at the center. And it goes on forever. So it's like a hyperbolic onion. Really tasty, those. All right, so that's all I have to say about surfaces. So that is part 1 of the summary. Ladies and gentlemen, part 2 of the summary. Limits. It's not such a big when we did it. It's sort of embedded in one of the chapters, but I'm giving it its own because the questions are quite different from the others. So you normally have 2 variables, but occasionally they'll throw 3 at you. Again, we'll see plenty of examples as we, I'm sure, in the Q&A part, but I just want to give you some general techniques for handling a limit in 2 or more variables. Okay, the first thing you should try is plug in the limit point. So the typical problem looks something like this. Limit xy goes to some point ab of f of xy. Okay, so the first thing is to plug in the limit point AB. If you get a nice answer, like not 0 over 0, if nice, you're done. That's the answer. And I have to say, looking at previous midterms, in every case I think where there were 4 or more limits, one of them was just a plug-in type. Occasionally there are 3 and 3, and one isn't, and none of them are, in fact. But most of the time, one of the limits is just a simple plug-in, work out the answer, and that's it. Okay, so that I advise is the first thing to try. The second thing to try, then, if it doesn't work, is maybe the limit doesn't exist. And normally the reason is because there are 2 paths that give you different limits. Okay, a lot of the time this is the case. Not always, and that's the third bullet point that I'll get up to. But I suggest that you do a reality check to see whether there are 2 paths. So try some paths. Maybe the limit doesn't exist. Okay, if the paths, the most common paths, so the most common limit goes to 0, 0. That's not always the case, and of course it might be 3 variables as well. We'll look at some examples later on, but I'm just trying to get the general ideas here. If you have a limit going to 0, 0, the easiest paths to try are, try x equals 0, that's a vertical path. That's like going along y, along the y-axis. And y equals 0, that's a horizontal path. Who knows? Maybe you'll get 2 different answers. if you get two different answers from those two paths, so this is supposed to be the origin in both cases. So. They don't really line up very well, do they? Oh well. Maybe you'll get two different numbers, and if you do get two different numbers, then the limit does not exist. The limit has to be the same along every path. So maybe that's enough. That's two different paths. If two different numbers, you're done. Limit does not exist. Now what do I mean try x equals 0? I literally mean plug in x equals 0 and then ignore x because it's 0. You just have a limit in y that's a one variable limit. And the same thing for y equals 0. You plug in y equals 0, y goes away wherever you saw it, and then you just take the limit as x goes to 0. So these are reducing the two variable limit to two one variable limits. Now if you do get different answers, great. However, if not, you could try. Otherwise, I would try some linear paths. So, by which I mean, try paths going like this, y equals mx. And you can intelligently choose the different values of x. So try y equals x, or y equals minus x, or y equals mx for some other value. For some m. If you don't even know what the m is, you can try m and see if the answer depends on m. Because if you can ever get two different answers, then the limit does not exist. Okay, so what I'm trying to say is, oh, look, you know, if 0 and 0 gave the same answer, try x, you never know. Try minus x, try 2x, I don't know, just try a few things. Get a feel for the problem. If you can break it, it's done. It doesn't exist. If you can't break it, then at this point you could try some more exotic paths, like parabola paths and stuff like that. This doesn't seem to come up. I can only see one example, I think, in the whole previous midterms that are online where you needed some exotic path. And I'm sure that will come up. But basically, most of the time, I'm sure someone will ask about it, but most of the time, we're still in summary mode. I suggest that if you find that all the linear paths come out the same, then probably the limit exists. Probably. Not necessarily, but probably you give up on this, and I suggest the third tactic, which is normally to try some sort of polar coordinates. So give up. No. Give up on 2. Give up on the paths. Don't give up. I'm not saying that. Don't quote me on that. I'm not going to be taken out of context here. Give up on the paths. Try polar coordinates. So the idea is that you have some limit like this going to 0. What you do is you put x equals r cosine theta, y equals r sine theta. And the limit becomes limit as r goes to 0 from above, because r can't be negative, of the same quantity, but with x replaced by r cosine theta and y replaced by r sine theta. So what this effectively does is, instead of doing a path, this kind of narrows us down to smaller and smaller balls of radius r. And that kind of takes care of every path, provided you can control the theta. Now, here's what I mean. First, I need some space. So if all goes nicely, by the way, this doesn't really work for 3 variables because we don't know polar coordinates in 3 variables yet. There is a polar coordinates, but we're not going to do that till after the midterm. 2 things can happen here. So the first thing that can happen is that somehow the theta goes away. Theta just vanishes or cancels out, and you just get a limit as r goes to 0 plus of just r. our stuff. Well, that should be fairly straightforward. Just treat it as a one-variable problem. Just do it. Solve as one variable. Hopefully you've done tons of those in your careers, calculus careers to date. Okay, so that's pretty rare. That's pretty rare that the thing doesn't have thetas, but it, you know, it can happen. Typically when you just have x squared plus y squared. That's what r squared is anyway. So if you just have x squared plus r squared floating around and there's no x's or r, or sorry, x squared plus y squared. If that's all it's the dependence on x and y, then the theta will go away and everything will be golden. However, the other possibility is that you'll have the limit as r goes to 0 plus, hopefully with something like r or r squared times theta mess. This could be r squared, etc. In that case, in order to really nail it, you hope that the theta mess only involves cosines and sines, so you really should use the sandwich principle. You really want that the theta mess is less than or equal to 1. Or 2 or something. So for example, if you just get it down to limit as r goes to 0 plus of, say, r squared, I'm not doing many examples, but this is even not a complete example. If you get something like r squared cosine theta sine squared theta, it's not really good enough to just say, oh, well, as r goes to 0, this goes to 0, because the theta could come and bite you. As it happens, it doesn't, but only because of the sandwich principle. I do this, cosine theta and sine theta. Clearly, this is less than or equal to 1. So let's just do this. That's clearly true. So multiply by r, which is a positive quantity, and you get the same inequality. And now you just observe that the limit as r goes to 0 of r equals 0, and the limit as of the I'm going to solve this limit. If it's negative r is 0. This thing is trapped in between two things that converge to 0. So this limit what's this limit? In polar coordinates, limit as r over theta. That limit doesn't exist. Because you could have a path that looks like this. Goes to the origin like this. In this path, remember, r is the distance from the origin, and theta is this angle. And as you move along this path, r goes to 0, but theta goes to 0 as well. And maybe that ratio is not 0. Maybe that ratio might be 1 in the limit. Or if the curve is really tangential, then that could even blow up to infinity. And you cannot use the sandwich principle there. So that's why I say you should use the sandwich principle. Although some of the official solutions don't even mention it. You should mention it. Be better than the official solution. All right. So that's all I had to say about limits. Told you this was going sort of nice. Okay, the third section I called before derivatives. But related to this, lengths, tangent planes, and approximations. I'm throwing them all in together because they're all very much related. Okay? So Oops, this is more like the first part of the summary where I had many, many bullet points. Well, not quite as many this time, but there's quite a few. So here are the things you need to know along these things. So first of all, curves look like this. They have a parameter. They are a vector. Normally you have 2 or 3 coordinates. In fact, in this course you always do. Depending on whether you're in a plane or in space, I'll write down the 3 coordinate version, but you have to be able to adapt. The velocity is the derivative, which is just the component-wise derivative. Okay, so you just take the derivative of each coordinate with respect to time, or the parameter. Okay, 2 important things about the velocity. Number 1, v of t is a tangent vector to the curve. At the appropriate position. So if the curve looks like this, actually I'll give you 3 things. So at this time, the position is r of t, tells you where to find the particle, but v of t, if you shift the vector so that the base is where the particle is instead of at the origin, v of t is a tangent vector to the curve, and the direction indicates which way it's moving as t is increasing, whether it's going that way or that way. If v happens to be 0, it's kind of taking a break. It could be an instantaneous break. So that's one important thing about the velocity. Another important thing is that its length. So that's the vector length. Is the speed. So the speed has to be positive or 0, cannot be negative. The velocity is a vector, the speed is a scalar. And finally, v of t over the speed. So that, of course, is a unit tangent vector. Occasionally, you also need the acceleration, which is just the derivative of v. Which is also the second derivative of the position, which of course is just the second derivative of each coordinate. And the geometrical interpretation is that this has something to do with the concavity of this curve, the curvature of it. And there's quite a lot in the textbook on it, but we didn't do it. We skipped it. So I am also going to skip it. Curvature, kurtosis, or whatever. Torsion, that's the word, not kurtosis. Torsion. I'm just mumbling. Ignore me. Stop ignoring me. Okay. I have to tell you the length of the curve between 2 times. The start time, well, that's just the distance. Distance is equal to speed times time, or if you prefer, distance is the integral of speed. That's my mnemonic. So the length is equal to the integral of the speed. So you have to find the speed. Of course, you can write this in terms of the square roots of the derivatives, but I really think that's the way to learn it. Most of the time the question anyway is find the velocity, find the speed, find the length. And so if you just learn it that way, it makes the most sense. All right? Again, it does rely on you being able to find the velocity and take its length. But that's how the formula should go. All right? So that's the basics about curves. Any questions about curves? Obviously no examples yet. It's the summary. All right.
Y, for example, of the velocity is negative. So when we integrate, we just turn the negative to positive and then
Okay, so the question is, what if some of the coordinates are negative? This is the length. This is the length of the curve. So remember, the length equals the square root of the sum of 3 squares. So it'll be x if there's 2. With 3 variables, you also have to insert. So your question is not pertinent because if some of the coordinates are negative, you have to take the length. It's not an absolute value again. This is a length. And I mean, it is the length of a one-dimensional vector, as in a number, but this is a vector, and so you should really think of it as a length rather than an absolute value. Okay? Another question. Would you be given t? Absolutely not. You would not be given t because you have to integrate. You might be given t0 and t1, but you have to integrate over all the different speeds. So you have to find a general formula. You'll have a general formula for r of t in terms of x, y, and z. You differentiate, you find a general formula for v. You take its length by the sum of the squares, and then the square root. And you have a general formula in terms of t, and then you integrate with respect to t. Okay? So you don't want to substitute first. You need to do a real integral. Does that answer?
The thing is, the length would then be, we have t inside.
Sorry, you have t inside the integral, yeah. And then you have to integrate with respect to t. It's a definite integral. You need to know the start time and the end time, and you'll get a number. That's the length. That's how far the particle has moved between time t0 and t1. It's the distance traveled. All right? Again, there are examples to be found. All right, you need to be able to take partial derivatives. And I want to remind you that you keep all the other variables constant. Okay, you know that. You also, of course, need to know del f or grad f is fx, fy, fz. If it's only 2 variables, then there's no third component there. Okay, so you need to be able to take second derivatives. That's clear. Okay, very important is the directional derivative. I know we've been going for a very long time without a break, so thank you for bearing with me. We will definitely take a long break after the summary. Okay, you're welcome. I thank myself. The directional derivative is this. Okay, you have, now this is a source of great confusion somehow. You have a function f. It describes like the temperature in space, or some other variable, but it's easiest to think of it as temperature. And you have some point, p, in space or in the plane, and it has a certain temperature. And you're interested in knowing if you stand at P and you start walking off in some direction or flying off in some direction, what is the change in temperature? Is it going to get hotter if I go this way? Is it colder? Is it whatever? And it all comes down to this. Grad f is a vector. It's actually a vector function because at each point there's a different value of it. But grad f at P, so this means evaluated at some point P, is a vector showing the steepest increase. Or in direction of, I should say, a vector in direction of steepest increase. So that means if I'm standing at this point P, and I want to say, how do I get the hottest? Where is the source of the heat? Which direction can I go in to find the heat? Heat seeking, that's the way I go. If I'm cold seeking, I go in exactly the opposite direction. If I'm neutral, I go in some perpendicular direction. In general, if I go in any direction, which I can just symbolize by a unit vector u. So I have this idea df, ds, that's just a code for the directional derivative. And it's at the point P, of course it's different at every point P, and it's also different for every direction you go in, u. And so the definition of this, I can't draw on top of my picture, is it's grad f evaluated at P. That's a specific vector, and you dot it with U. So if U happens to point in exactly the same direction, then you'll get the positive number. If it points in the same direction as grad f. If it points in the opposite direction, you get a negative number, and if it points in an orthogonal direction, you get a 0, which means the temperature doesn't change in that direction, at least not when you first head out in that direction. For an instant, it's the same temperature. All right, so another way of looking at this is that it's the length of the gradient times the cosine of theta, where theta is the angle in between grad f and U. Now I want to emphasize here, U must be a unit vector. So when you apply this formula, you need to use a unit vector, not a regular vector. If you have another vector, you have to divide by the length. Remember, this is one of the first things I said, to make a vector into a unit vector. So occasionally you need this cosine version of it. And the reason that you don't have the length of U there is because it's 1. You could put it in, but it's a unit vector, so it's 1. Okay, so the point of this, I'll tell you the most common question. Without actually doing an example specifically, I'll sort of set up the general type of example that seems to come up with this. All right, here's an example. Okay, so typically you have some function, you have some curve. This is just the general form of the example. So you have some curve in space, not necessarily a line, and you have some magical value of t that you care about. Or some point is given, and if you have the point but not the t, you have to then plug in and solve to find t. You're going to need to know t. Either they give it to you, or if you know the point, you can normally find the value of t that solves the equation. You have 3 simultaneous equations just in one variable, so you ought to be able to solve and find that variable. Okay, so given this, what you're asked for is, at this point, at this time or this point, or point, the same thing, as in when you're here, is it getting hotter or colder? Is F increasing or decreasing? And the way to solve it is exactly find the ingredients of this. So first, find the gradient and specialize to this point you care about. By the way, if you know t, then you find x, y, and z by plugging in t. If you know x, y, z, you plug it in and find t. So, you know, either way, you have to plug that in to get delta F evaluated at P. This is called P. So that's step 1. Step 2 is you find the velocity vector. So find v of t and plug in the value of t to get your velocity vector v. So the curve goes like this. You know where you are, you just need to know where you're going. And to do it properly, let u be v over the length of v. So that's the unit version. And finally, df ds, which is what you want, the change in f, at the point P in the direction U, you use the previous formula. That's from step 1. And then you dot with the U from step 2. And you get some answer. If that answer is positive, F is increasing. Getting hotter, if you like. Negative, it's decreasing. But now, you see, unlike regular variable calculus, you don't just have an increasing function or a decreasing function. It all depends which direction you go. And so with a curve, you need to calculate its velocity to find out the direction. That's the most common omission that students seem to make when solving these problems. They have the curve, they calculate the gradient, they plug it in, they do step 1 just fine. It's step 2 where you get fouled up. So actually, one little point. For this question, you don't really need to divide by the length of v. You won't get the correct directional derivative, but the sign, as in SIGN, positive or negative, will be unaffected. All right. Any questions about that? All right. Chain rules. Make sure you know the chain rules. They don't come up very often. But I didn't see any in midterms, but there was a question on the Fall 04 final. Make sure you can do it. It's on the website. You may not have looked at finals. I kind of approve of not looking at too many finals. You kind of want to save those to practice for the final. But they do something, look on some of the old ones, they do have some nice problems that are pertinent to this midterm as well. So make sure you know that. Sometimes you have to differentiate implicitly. So, for example, there might be 3 variables. You might have an equation that looks like f of x, y, z equals 0, but you might be given that z depends on x and y. Then you can't really legitimately take a z derivative because z is not really an independent variable. So the way to do it is if you differentiate implicitly both sides with respect to d dx. Of course, the right-hand side is 0 in this case. But if you do that and treat y as a constant, but z not constant, z is z of x, then you can find, this will find z dx, at least after solving. So then you can solve dz dx. Man, this is a big course. I've never done this before. This is the first time I've ever done this summary. And I just thought it would take an hour. Ha! You guys are screwed. No. I don't mean that. We're nearly done. We're nearly done. This is bounded. This is a bounded course. Okay. All right, so again, we can look at some examples of implicit differentiation later. All right, I'm really close. Tangent planes. If you have a surface, okay, please. F of x, y, z equals c. The tangent plane at some point on the surface, the normal is just grad f at that point. So in other words, the plane looks like this. It's the x derivative at point times x minus x0 plus the y derivative at that point times y minus y0 plus the z derivative at that point times z minus z0 equals 0. So if you look back way at the beginning of the summary, for the equation of a plane through x0, y0, z0 with normal ABC, the only difference is here the normal is fx, fy, fz, which is the gradient, but evaluated at the point P. So again, P is x0, y0, z0. So that's the formula for it. No examples, it's the summary. If the equation looks like this, z equals f of xy, that's a sort of variant of it, then you can reduce it to the other one by writing f of x comma y minus z equals 0. And then the derivative in the z direction will be -1. So explicitly, it becomes fx at p, and here now p is x0, y0, z0 again. So fx at p, let's call this p1. You ignore the z. So there's no z, but I mean basically it's just an adaptation of the other one. And the difference is that the z derivative is -1. So z derivative. So I actually don't like to remember this separately. I kind of just reduce it to the other case and consider a free variable function here where the z variable is only expressed as a -1 derivative. All right? So that's the tangent plane. All right. Tangent line to curve. Suppose you have a curve which is an intersection of two surfaces. So actually we saw a Lagrange multiplier problem like much earlier. Was it last week? Last year? No, earlier today. It just seems like a long time ago. We saw two surfaces intersecting. Suppose you want to find a tangent line to the curves. It's quite simple. The two surfaces might be f of x, y, z equals c, and g of x, y, z equals c1, some other number. All you do is you compute the two normals. So v is going to be cross because these are the normals to the two surfaces at the point P that you're interested in. So the tangent line's got to be perpendicular to both of them. So you take the cross product and you get this. And that's the V. And then you just need the point on the line. So R of t is your point P plus TV. That's it. So you already know the point because it's given in the problem. And you just need to find that vector V that's along the line. And that's just the cross product of the normals. Okay? Now, we finish off topic 3. Here are 6 types of approximations. Change in F. Direction U from P, distance delta S. Okay, so you're at a point P, the function has a certain value. You want to go in a certain direction by an amount delta S. How much does the function change? You just use the directional derivative. Delta F is approximately the directional derivative at P comma U, and we computed the formula over there, so I'm not going to rewrite it again, times delta S. So that's a good little approximation formula. It makes a lot of sense if you look at it. So occasionally, once in a blue moon, I've seen that. This is not a cross product, this is just a regular times. It's not even a dot product, it's a multiplication. All right, so I've not seen that come up very often. You do need to know the linearization. And in 3 variables, what the hey? You get the function value at this magical point you get the x derivative at the same point times x minus x0 plus the y derivative at the same point, y minus y0. And you get the z derivative times z minus z0. So that's the formula for it. You need to know it. You need to be able to produce it. If there's only two variables, you don't have that last term. You just find the gradient, but you also need to evaluate the function, and you plug it in. That's an equation of a plane, which is a tangent plane. It's actually the same equation. So in two variables, z equals L of xy is the tangent plane to z equals f of xy at x0, y0. Good to know that. Okay. Another approximation, which I'm not even going to talk about because I talked about it earlier, and if you did miss it, you should get it from L1. If you're on the video, you just have to rewind somewhere. Taylor P2 of xy. I wrote up that formula and gave an example. It correctly belongs here in my summary as an approximation. It refines the linearization by adding a quadratic term. Error in linearization. I've never seen a question on it in the midterm. So I propose that if you are keen or risk averse, you should try to learn this. But I don't have time to do it now. Again, later we might have some time for the problems. So I'm just going to have to skip this. Total differential. Again, I can't think of any questions that I've actually seen, but df, it's very similar to the linearization. Well, let's write it like this. That just tells you how much f changes approximately when x changes and y changes. So f depends on, this is a two-variable version that I'm writing down to save chalk. So if x changes a little bit and y changes, then f will change a little bit. So this is an approximate change in f. So if you change f by, well, here's the change in x. So if you increase x by 0.1 and you decrease y by minus, by 0.2, you compute these derivatives, plug that in, and you'll get the overall change in f. Again, I haven't seen too many problems. Just if you do happen to get a problem in that realm, then remember that the relative change, percent change in x, this is a useful little aside from single variable calculus, is dx over x times 100%. That's a useful little fact. And of course it works for other variables as well. So the definition of that is dx over x. That's the approximate percent change. And of course 3D versions of this work as well. So those are the approximations. All right, that's the end of section 3. Section 4, max min. Again, I did almost all of this in the first hour of this, or first hour and a half, or however long it took. The only thing that I did not do is classify the critical points. So in addition to what I did, in addition to the first section of this session, the only thing left is classifying critical points. Okay, so here's the second derivative test, and then that's the end of the summary, actually, believe it or not. So here goes. Suppose you have a critical point with f of x equals f of y equals 0, and you're asked to classify it. Here's what you do. you compute the Hessian. Well, compute this. fxx, fyy, and then the mixed goes here. And it's a 2 by 2 determinant. At this critical point, you have to plug in the values in. So let's say the critical point is at x0, y0. Plug in x0, y0, and take determinant. Take the determinant of this matrix. And you have to repeat this if there's multiple critical points. You have to repeat for every critical point. So you compute this, you plug in, and you get the determinant, which you call h. And then here is the roadmap. If h is positive, then you either have a max or a min. It's a local max if either of these diagonals is positive, say fxx, and it's a local min if, I'm sorry, I got this the wrong way around. Maximum is when the second derivative is negative. Minimum is when it's positive. So if the Hessian, the determinant, turns out to be positive, you say, it's a max or a min, and you just check the sign of that upper diagonal element. It cannot be 0, by the way. If that's 0, then this times this is 0, and this is a square, so the determinant will be negative. If, on the other hand, h is less than 0, you have a saddle point. So that's like a point of inflection. In some direction it's like this, and in the other direction or some other direction will be like this. It's neither a local max nor a local minimum. Unfortunately, once in a blue moon, h equals 0, and then you're in some trouble. You really have to fudge around. You cannot use this test. You have to search for points near the critical point and just see whether it's a local max or a min. So you just sort of got to fiddle around. They could ask it on the midterm, and there were one or two examples. Again, it will have to come up in the questions. All right, any brief questions about that last little bit? Sorry? Okay. That's the end of the summary.